patient with the bit of a setup. But today we'll talk a little bit about what Aleo is and why is it needed, and it's building a secure version of the internet. So we'll spend around 20 minutes understanding the philosophy behind building Aleo and how it functions from a technical perspective. And then towards the end of it, we will be looking at some code, doing a deployment on Leo. And at the end, there's also a small, you could say, takeaway for you to complete the code to deploy it on the chain that qualifies you for a reward. Because the idea of the workshop is for you to build or deploy your first program right here. And we'll be looking at an auction program. So the idea is that you should be able to make a few bids in an auction, and then resolve that bid, finish it, and then claim the prize. So that's what we're going to do, and we'll do that with you today. A little bit about me. My name is Laisha. I work as a Devil Ambassador with Aleo, and I've been in the Web3 space for around 2 years now. I've dabbled with different things from DeFi, security, and I was an ML engineer before coming into this space. Moving on. As I said, Aleo is building a more secure internet. And by that I mean it's a layer 1 privacy preserving blockchain. Now, why did we need that, and how we're achieving that is what we're going to do for the next 20 minutes. So, taking a step back, let's just quickly go over some of the terms which are the foundation of whatever we are going to talk about today. Now, when I say privacy preserving, obviously there is some sort of cryptographic process that is doing that, and that is zero knowledge proofs for us. Now, ZK and zero knowledge proofs are not new, they've been around for a while. It is now that we are using them practically in the Web3 space. They're very simple. All we are trying to do is prove that I know a certain piece of information without revealing what that information is actually. And as the term goes, there's always a concept of someone who's trying to prove the information, and there's the other party to whom I'm trying to prove the information. So there's a prover as well as a verifier. Now the idea here is, in the real world, the information we're trying to prove will not always be simple and straightforward. It can be big data, it can be a bunch of numbers. So there has to be a sophisticated way of doing it. And we have two ways in which zero knowledge proofs are made, where one is Starks and the other is Snarks. Aleo as a blockchain is Snark based. And just to give you a little bit of a simple example of what zero knowledge is, if we look at it from a very high level, Wordle, which is a popular game by New York Times, is a very simple example of that. Because every time you put out a screenshot saying, I've solved today's puzzle, you don't reveal the puzzle, but you do have a proof that you actually completed it. But again, this is very simple. So, as I said, Aleo is a chain that is based on ZK Snarks. Let's break down Snarks a little bit. We won't be delving into why Snarks was chosen over Starks, but it's important to just understand what ideology Snarks come with. If I break down the Snarks, there are three important things. One is succinct, non-interactive, and argument. Succinct means that the proofs are small and fast to verify, which is, you could say, a USP of Snarks. And non-interactive means that it's a trust-based system. That means when I'm trying to prove a set of information, there's no interaction between the prover and the verifier of any sensitive information. So it's a trust-based system, and hence it's also fast. And one thing that holds for Snark is the argument, which means that in any case, if I am a prover or a verifier and I'm trying to bluff the system, this should be identified within a finite amount of time. So you could say it's a bounded computation. But why is this important, right? In order to understand where Aleo comes in and why Aleo as an ecosystem is there, we need to go back a little bit on the timeline to understand what happened when we started with centralized systems. Obviously, there was centralized control of power, and we wanted some digitization or autonomy. So we started with digitizing the movement of money. We saw the rise of DigiCash, Hash Gold. These were all ways in which you could digitize your money in a not so decentralized way. And that's why when Bitcoin came, it was the first revolutionary way in which you could actually move money. But by money, I mean only a specific sort of currency, which was localized to Bitcoin. And when Bitcoin came, it was all public. right? So the people needed some sort of privacy on top of it so that they can do their transactions better. And that saw the rise of Zcash. And Zcash was one of the first ways in which you could have a privacy over your transactions. But then again, the problem was that while there was privacy, you couldn't do much, right? You could just send money from one place to another. That's when Ethereum introduced the concept of virtual machines, where you could club your interaction with the chain along with some sort of logic that decides when to do, what kind of transaction to do. Now, when Ethereum came in, it had its own share of issues in terms of scalability, financial times, and as well as just the number of features it had. So that also led to other chains coming in, each trying to solve one of the problems, right? Cosmos, Polkadot, Nearall tried to solve different problems of scalability from different perspectives. So the ecosystem was, one was Bitcoin, which gave the security, but not a lot of programmability. But then there was Ethereum, which was very programmable, but it was all public. So there's an empty space where Aleo comes in, which gives you both security as well as programmability. And how it does that is, one, there is a concept of zero-knowledge executions, which is also, if you look at the Zcash time, when the Zcash team was developing, so a lot of the tech draws inspiration from the Zcash papers that have come in, so zero-knowledge execution is derived from that. And then there is also the concept of private computation, which means that you do not really need to necessarily run your entire proof generation part on chain. You actually do the proof generation off chain, and only the verification of your proof is happening on chain. So that's how there are two distinguishing features that Aleo has. But before that, this is the missing gap I was mentioning that Aleo fills in. And until today, I mean, before Aleo, there was not a chain which was able to give you the kind of interoperability and privacy before. But what I want to come to is two things. So there is zero gas fees needed for private transactions. And when I mean private, it means that any transaction which is computationally intensive and not changing the state of the blockchain, you do not incur any gas because all of your computation is happening offline. Only when you are verifying the proof, which is much lesser of a computational activity, you need to go on chain, which also means that you practically have unlimited runtime. Let's take a simple example. Let's say I am running a machine learning application where I'm trying to verify the biometrics of people in my application. Now that's a computationally intensive process, right? If I were to do that on chain and run my circuit and the entire logic of proof generation, I would incur a lot of gas. What Aleo does is that the proof generator works offline, sends the proof on chain, verification happens, and then the transactions propagated onto the chain, and the proof is verified, and then the validation happens. So essentially, there are two kinds of proof of, like there's obviously proof of stake, but then there's also proof of succinct work, which means that your prover has to work hard enough to generate the proof, and they get awarded in Aleo credits. So both work on different mechanisms. The validators still function the way your regular validators work. Their job is to make sure that the transaction that has come in has a verified proof attached to it. Now, when I talk about unlimited runtime and I talk about zero gas fees needed, it's also important to understand that given these two paradigms, practically as the number of executions increase, the cost of execution increases in the traditional blockchains. But that's not the case here because the number of executions is not necessarily dependent that all of them are going to be on chain. So over time, the cost can actually flatten out. And that's why building privacy within the chain is advantageous because you do not need to have another tech that builds out the privacy part for you. That can be incorporated within the code logic for you. But now, with all of these functionalities, let's understand how you as developers or you as an ecosystem can get started with building on Aleo or in general contributing to Aleo. Now, there are three things that come in. For a developer perspective, if you want to start building on Aleo, you start with the Leo language. It's a Rust-based DSL. What Leo does is that it abstracts away the complexities of writing circuits in general, so it does the heavy lifting of building up the logic that you need for writing private applications. And then you have SnarkOS and SnarkVM. So when I was mentioning proof of succinct work, so Snark OS is what takes care of that. Like basically you can run your own local Leo node, you can also become a validator. So all of those options are available and we'll look at how you can do that. And Snark VM is the virtual machine that has been built that processes your Leo code, breaks it down into instructions and then propagates the logic into the chain. We'll also look at that of how it's done. But to give you a brief overview of the ecosystem, what we looked at was just the infrastructure layer. If you want to build dApps, full stack dApps, you also have the SDK using which you can build proper applications. And we have a bunch of applications, these are just some of them. We have around 300 applications that are there, and they span across different verticals within this space. So coming to Leo. Now, we are pretty used to the fact that there is going to be a program that's going to get converted into bytecode, and that bytecode, there are opcodes that are derived as a gas estimation, and that is how your program gets generated. Let's say I have a very simple program where I'm saying A plus B is equal to C. Now here you see that the private, there's a keyword called private, which means that I don't want to share what my final output is. So what essentially happens is, the first time your Leo program goes to the virtual machine, it's gonna go and generate the proof for you, which either you can do or you can delegate it to a prover to do it for you. And then your Leo program is actually converted into Leo instructions, which you could say internally gets converted into bytecode, which then gets understood by the chain. Now here, what is important is that if you are someone who is coming from a Rust ecosystem and you want to do things at a more compiler level, you can actually use the Aleo instructions that are generated and optimize your code for further things. So you're not necessarily dependent on doing things at a high level, but if you want to go one level down and optimize your program for other things, you can work at an Aleo instruction level as well. We'll look at when we actually run the code.
So the AVM is the same as Snark?
Yes, yes. So, I mean, essentially it's Aleo VM or something. So for example, if you're writing a simple program where you're trying to do A plus B is C, so this is how it will look in Leo. So program hello world.aleo is essentially the header, which defines that this is a unique program that's going to lie in the bunch of programs that I have, which is generally called a registry. And the concept of functions is different in Leo. Essentially, we have transitions for anything that we are doing off-chain. So any computational work that you are doing, you can necessarily do it inside a transition. And one transition can have multiple transactions, which could be, either an addition logic, could be a computational logic. So here it's pretty simple. By default, all the variables that you're seeing are private. So until I specify the identifier of public, it will be considered private. So I have one public variable and then my output, and the other variable is private. So when I have the intermediate stage, the instructions are going to look something like this. My R0 is public, which is essentially the storage slot where they would be going. And then my second input is private and my output is also private. And this is the instruction that I want to add R0 and R1 into R2. So it's very similar to how you have assembly level instructions. And that's why it gives you the autonomy of working at both a high level language as well as you can optimize Rust level instructions as well. And another thing that is important to highlight before we start looking at code is going a step back and looking at two ecosystems that we evaluated. One was Bitcoin, which works in the UTXO model, which stands for unspent transaction outputs, which is similar to how you spend your cash. For example, if I have a $500 note and I want to pay $350 to someone, I'll actually give the $500 note, they'll deduct $350 and give me $150 back. So now, instead of one $500 note, I have one state which represents the $350 deduction, and I have one state which represents the $150 balance I have. And that's exactly how UTXO works. And then we have the traditional account model, which is the EVM space, where there's a global state. So at any given point of time, if I want to understand what my balance is, I can check it against my address. What Aleo's record model does is that it draws inspiration from the UTXO model. And at any given point of time, the record has information about all the other records. Now UTXO, if you look at it, can only have information about the balance unless you build another structure on top of it. So that's what record does. Record is not just limited to having information, but it can have a lot of other metadata as well. So essentially, every time you are doing a transaction within the network, you are either consuming a record or you are creating a new record. And that's why the concept of transition is there. Transitions are meant to either create a record or consume a record. And that is the paradigm on which Aleo or Leo as a language works. And just to give you another overview, when I spoke about SnarkOS and SnarkVM, so SnarkOS is where the validator would lie. So the consensus, the node operation, all of that is handled by SnarkOS. And provers, which do the heavy lifting of generating the proof offline for you, happens in the SnarkVM. And this is just an overview of the life cycle. So let's say I am someone who has sent a transaction into the network. This is what we are generally used to seeing, right? A transaction is coming, it goes into the network where the validators are my node operators. They come to a consensus and then my transaction gets deployed. But there's something else that is happening inside within this block. So if you look at it, there's something called as a program registry. So we don't have smart contracts in Aleo, these are called programs. Each program that you deploy has to be unique because they lie in the program registry and are defined by the program code that you have. So let's go and look inside this block as to what's happening. So when I'm requesting my transaction to be validated and added into the block, I first need to have a proof associated with it to make sure that my transaction can be validated. So either I can run the SnarkVM and be my own proof generator, or I can delegate it or run some cloud infra, AWS infra to generate that proof. The proof generated is then sent along with the program code that you had evaluated, which is essentially the Aleo instructions, into the network. Then the proof is verified, and using the bytecode of your code, your transaction gets validated and then added into the network. And essentially this is what a standard flow of information would look like in a dApp. So instead of now just the execution response being validated by the validators, you will have an additional step of having provers, but making sure that this is all offline. And Aleo as an ecosystem gives you the autonomy to choose what are the things that you want to do off-chain and what are the things that you want to do on-chain. And we look at how we achieve that. And yeah, this is just a comparison comparing the Ethereum space and the non-EVM space with Aleo as an ecosystem. To give you a little bit of an insight into the kind of projects we have. The projects we have span across different verticals. Gaming, ZFi, tooling, these are some of the popular verticals. Primarily, DeFi as a field benefits a lot from the core principles of Aleo. That's why you'll see that there are a lot of different dApps in ZFi. We have a bunch of different wallets like Avail and Puzzle that are available. We also have a native Leo wallet using which you can manage funds, also manage your deployments, and do a bunch of other things. So let's get started with coding. How many of you here have some sort of Leo setup already? No one? Oh, that's all right. Even if you don't have it, you can do the entire exercise with me on Leo Playground. So Leo Playground enables you to run your programs, compile them. However, you won't be able to deploy the program. For that, you will have to install Leo in your laptops, which you can obviously do a little later, but I'll make sure that the instructions and the entire process of how to do that is sent across to you through the right channel. So you can go to this link, tinyurl.com/Aleo101. This has the setup guide of how to set up Leo in your system, and it also has the basic instructions of how to run a program.
Sorry, what's the Wi-Fi?
The Wi-Fi is, I think, LC, capital LC, and the password is
Capital LC
center. Someone can write it on the whiteboard, maybe.
Thank you.
Okay. And all of the code that we'll be using today can be found on this. So as I said, we'll be building an auction application on Aleo where we'll try to generalize the auction so that you can go and run an auction of your own. So you can take a note of this link as well so that you can follow along. If everyone's ready, let's get started. So this is the link for the Aleo playground. So you can go to this link, and then we'll start with a very basic program of adding two integers, and then we'll go ahead and run our auction application. So if you go to the playground, it will look something like this. Alright, let me walk you through how the structure of a Leo projects look like. So when you first set up a Leo project, while here it's already done for you, but let me show you how you can achieve that when you have the Leo setup done. Is the text visible? Is it big enough? Okay. So once you have the Leo setup, you can quickly verify if Leo language is installed using Leo. And if you see the available commands, that means you're good to go. So if you look at it, there is a command called new. So let's say if I want to write a program, say hello world, which we do in pretty much every language that we start learning, it will initialize a simple program for me. So let's look at the structure, and then we go ahead and run one of the programs that we just saw on the playground. So if you look at the left side, there's a source, and then there's a file called main.leo. Now, main.leo is the entry point, right, where we start the execution of our program. So everything and anything that you want your program to do lies here. If you have other utility functions that can lie in another file, you can import it here. The first line is called program hello world.aleo. Within this, the entire logic of your code will lie. But this program is always a unique name, and how it identifies it is there is a program.json file, which infers the name of the program that you're writing, which you have to make sure should always be unique. In case you are working with the SDK or any other tools, that will come under your dependencies. For now, for the simplicity's sake, we'll just skip that. When we look at line number 3, we say that we have a transition, main, which is the name, and then we have two inputs, sorry, A and B, which we just discussed. So the idea is that I have two integers that I want to add, and I don't want my output to be visible to anyone. So if I have to run this particular program, how do I go about it? So there are two commands which are really important in Leo. One is to build your program, because if you look at the code, this is a bunch of high-level instructions, which I understand, but my compiler doesn't. So when I run Leo build, it actually does the build, it generates the instructions which are then passed to the virtual machine. So if I go to the source and look at this file, so essentially, let me show you. And another important thing to note here is that Leo is a typed language. That means you will have to specify the types of each variable that you're working with. Just give me 1 minute. So if you look at the input, it's an unsigned integer 32, and the other input is also unsigned integer, and then the output is unsigned as well. So when we are passing our input as well, we'll have to specify the types. And the transition I'm trying to run is main. So I specify the name of the transition, then I specify my inputs, and then I run it. So the output is 3U32, which is what we expected. Now once we have run this, let me go back to the code. There's also one more thing that is important to note, is that when you initialize your project, it comes with a pre-configured environment file. Now why that is important is because it specifies what network you're on, and the private key when you're deploying your program, and then it's the endpoint that is used to broadcast your transaction into the network. We'll come to that a little later. Okay. Now when I run Leo build is when I'll be able to see my instructions. So I go into the build folder and then I open it. So it translates my logic into Aleo instructions. Now this was a very simple logic, right? I had to just add 2 integers and just make sure that I'm able to get the output. Now if you want to do the same thing, you can do this in Leo Playground. You can go to the playground and it will by default initialize the project for you. You have a terminal available in the second half of the page and you can run it and you can change the inputs from like of your choice. If everyone's able to do that, can I please get a raise of hands so that I can go on to explain the auction program? Okay, that's good. Now we have understood 2 paradigms here. One is the concept of transition. Now if you look at it, we have not done anything on chain so far, right? We just did a simple execution, right? A simple computation. We'll also look at how do we achieve on-chain transactions and how do we go about it. And in order for us to build an auction, let's understand what we need. We need some sort of an auction entity within which I can place my bids. I need someone who should be able to resolve the auction for me, so an owner of an auction. And I need to define some sort of structure for the bid. And the process will look something like, for the simplicity's sake of it, we'll assume that all bids are coming in a sequential order and are resolved based on time as well. And then in this case, I'm just going to demonstrate 2 bids. So whichever is the highest wins. And the owner of the auction will be able to resolve the bids for us. So let's go ahead and look at the code. If you want to run the simpler version of auction, you can go to examples and choose auction from here. And you will be able to see the auction code. So you go to source folder and open this. So this is a simpler version. So first let's look at this and then we'll understand how Aleo as a language helps you achieve not just simple programs but like advanced programs which you can use for applications at scale. Now as I said in the beginning, right, Aleo introduces a new model called the record model. Now what exactly is a record? Record is nothing but a data structure that helps you hold the information about the ownership as well as any metadata associated with it. So, as I mentioned, I want to run an auction and the entire auction depends on what kind of bids are coming in. So I have created a record called bid and these are some of the fields that are there. I've added a field called owner of type address that makes sure who the owner of this record is. Then I have another field called bidder. We'll understand why we have 2 address fields and not just 1, because there's a way in which we are resolving our auction and that's why we need it. And then we have standard variables called amount, which defines what is my bidding amount and then whether I'm the winner or not. So it's a Boolean variable. So the first thing I need is I need a functionality with which I can place my bid. Now when I place a bid, right, as I mentioned, you can consume or you can spend a record using the transition function. So we start with creating our first transition, which is called the place bid. Now when I'm placing a bid, I want to be able to understand who is placing the bid and what is the amount for which I'm placing the bid. So these are the only two arguments I need. When I do this, I need to make sure that the person who's calling this function is actually the bidder. What I'm doing in the second half is generating a new record. And you can do that in a transition. Now, when I generate a new record, it's essentially placing a bid for me. Wherein, if you see, owner is a static address. Why that is there is because I have predefined a set of public-private key pair. That is the owner, which is me, so that I can resolve all the bids using all of the records that have come in. The bidder is my address, the amount is picked up, and by default, I am not the winner. So I can place multiple bids using this. For the simplicity of this example, it's just 2 bids and we're not using any array to store it in a structure. But once, let's say, I have 2 bids, right? Obviously, the one with the higher amount wins. How do I go about resolving it? Obviously, I'm interested in comparing the bid.amount field and make sure that whichever is greater goes ahead and is declared as the winner. So let's look at the resolve function. Now, in my resolve function, as you can see, there are 2 records as input. One is the first and the second. In a more practical scenario, you'll obviously have an array here which will store all of the records. But essentially, I need to first make sure that whoever's calling this function resolve is actually the owner of the option, which is this address that I have pre-decided. You can choose a pair of your choice. And then all I need to check is if the amount is greater for the first one, they are the winner, otherwise the second one is the winner. And that's about it. But this is not where your auction will end. Why? Because even if you have won the auction, your record is still owned by the owner of the auction. So you cannot claim your prize yet. So in order for you to claim your prize, you would have to give back the ownership to the person who had given the bid. It's very similar to how actual auctions work. You need to go and give a proof that you are the one who actually did the bid. So for giving back the ownership, we have a finish function, which is also something only the owner of the auction can call. So we are just doing an assert call, making sure the address that's calling this function is the one which is defined as the owner of this auction. And when I return the record back, both the owner and the bidder will be the same address, and winner will be marked as true. Now, as I said, this is a simpler version, right? You can make 2 bids. You cannot run multiple auctions using this, and this is just restricted to one auction. What if you wanted to build a generic auction where you can have or run any kinds of bid, you can resolve it faster? So we'll look at that. And with that comes another concept of async await functions. Now, async, as the name suggests, is an asynchronous call, right? Initially, before, there used to be a concept of finalize keyword, which was used to execute on-chain operations within Leo. Because right now, all that you see is a transition. Nothing here is actually happening on-chain, because this is just the computation of logic. If I want to post the results of who has won the auction, I would want to post this on-chain. And for that, I would need a finalized functionality. But in order to enable this more autonomously, there's a concept of async and await, where when I make an asynchronous call to the network to do a computation, it generates a future. Future is a type that's supported in Leo, which holds the computation output of whatever I've done. And then I can make an await call, which fetches that future object from me, and then publishes that to the chain. Now I know that's a lot of information, so let's look at some code that makes it clear for you. Alright, so as I said that we're not just having a bid, but we also have an auction, because I wanted to make it generic, so I've added an auction. So what my auction has is who is running the auction, very simple, who is the owner. I have a title to define what the auction is, whether the auction is completed or not. Again, this can be a time-based field if it's more suited to your use case. And I've added another variable called whether the prize is claimed. Now this is important because this is what you would need for your workshop to be able to qualify for a reward for this workshop. And And another important thing is, now our bid record is having another field called auction ID, so that I can understand what are all the bids that were made within this auction. So you can run multiple auctions from the same field. Now when I do that, I need to make sure that every auction that I run from this program should be unique. So I need to have a unique ID every time I run it. In order for me to do that, I have an initialization function. Now if you look here, there is an async transaction called int auction. Now this async transaction's job is to run and initialize a transaction ID for me, which is nothing but a BPH 256 field. And we don't have the concept of strings, but we have the concept of field in Leo, which is more optimized for the Aleo instructions. And what you see in the next line is essentially what does the job of calling this function, and I've called it finalize because it holds or it sits well with the finalize ideology that was there before. So actually what's happening is, when I want to initialize a new auction, I'm going to make sure that my runner is basically the address from which this call came. The title is whatever was passed, and whatever ID I passed in the beginning is coming as an argument. So essentially this is the constructor that is there. What the async call does is that if you see, the name of both the functions is same, right? But the second function has a finalized suffix, which tells the function to consume the future record that was generated. And how it works is that this async call generated the record for me, and it's present. And then I'm calling this particular function from my async transition. So the job of the transition function is to either create a record or consume a record. The job of my function is to facilitate that utility for my the transition. Why is that the case? Because within your transition, you're not restricted to just do one transaction. You can do multiple number of transactions. So say if you had probably another level of hierarchy above it, probably you are running multiple auctions in a program and you want to initialize a program as well. So you can do that within this. So you can have multiple records being generated out of one transition. That is very much possible. Another thing that is important here is the concept of mapping. Now, why I have a mapping is because since I have one program which is managing multiple auctions, I should be able to make sure that I'm able to maintain the history of all my auctions that I'm doing, and the same kind of auction is not created again if the random number generates the same thing. The rest of the functionality is essentially what we just saw. But how is this different? Is because the way we are calling it is slightly different. Let's look at the finish function, because I don't want my bids to be there on chain. I also don't want my resolve function to be on chain, right? I can resolve it offline. What I want to be on chain is when I'm declaring the results. I need my options to be on chain, I need the results to be on chain. Bids necessarily don't need to be on chain. I mean, it would unnecessarily take more space. So when I'm running my transition resolve, I have, the finish function. I have a finish finalize, which does the job of publishing those results on chain. Now how I do that is I define my main logic of updating a record for the auction within my finalize function. But when I want to publish it on chain, I need to make sure that there's a transition. So what happens is, the logic is when you have a transaction, a finalize function should follow with the same name and a suffix called finalize. So your actual logic of the code actually lies in your transition, which is done offline. The finalize function does the job of publishing information onto the chain. And what I'm doing here is essentially updating my auction and making sure I'm also returning the bid to this function so that it can be resolved. And the logic, if you see, is same as what we discussed. The only additional field we have here is audition ID, and we also have another field called mapping. Now for the simplicity of the workshop, you can actually submit the contract using the contract that is available on the playground. Let me go with that, because it is likely that some of you do not have the probably some of you do not have the installation done, so you should be able to at least compile it and do it. So you can go to the project, go to option, and use this particular code. Because that's just an optimization. The logic is same. But now I want to show you how it works, right? Let's just run this auction properly. So let me walk you through these steps, right? If I'm running an auction, I need 3 entities, or rather, let's say 3 accounts. One account is the main account, which is the auctioneer. Then 2 people who are independent bidders. So I cannot see your bid, you cannot see my bid, but the auctioneer can see the bid as long as he is the owner, right? So what I've done is I have created a bash file that has the commands. So let's quickly look at that. Let me open this in VS Code, or let's just do it here. We can skip the first few lines of it because this is just letting us know that we are setting the necessary variables in our environment file. But just make sure to read through this. There are 3 accounts that we've created. That's why there are 3 different private keys that are present. So when I want to initialize an auction, I want to make sure that my environment file has the private key of the owner. So the first thing I'm doing is making sure that I'm updating the private key into my environment file. Now when I want to place the bid, I need to call the place bid function with the environment key updated in my end file. So I updated the environment key. Now when I want to call the place bid function, if you look at the structure of it, my transition is called place bid. And there are 2 arguments. One is of type address, one is the amount. And that's essentially what I'm passing. So this is my public key, and this is the amount, which is type U64. Let's say you are changing the type here. The type in the argument should also change. And when you want to place the second bid, let's say I'm placing a bid of 90. I swap in my other private key because then I should be the bidder and not the other record. I place another bid, I update the amount. Now, when I want to resolve this particular auction, I would want to update the environment key to the initial one who had initialized the auction. So, in order for me to call the resolve function, I have to first update the private key. And when I call the resolve function, let's go back to the code. There are 2 inputs, and both are of type bid, which means that we need to pass the actual record which was generated from the place bid. And how a record looks like, let me just run this Leo run place bid. When you run this, you're essentially returning a record where the owner is your public key of basically the auctioneer, bidder is your address, whatever amount you passed, and since we are considering that we do not want to disclose our bids, you see that there's a suffix called .private, and is winner, which is currently false, and nonce is what makes sure that each record is unique and the network can understand how to consume it and how to propagate it. So when I want to call my resolve function, I'll essentially be passing the same record that I got from my first 2 computations, which is the record for 10 and the other record is for 90. Now essentially the winner is B. But how is this happening? So these are 2 bid records, I'm just inferring the amount and I'm comparing it, and this is the winner. So when I run this, let me just run the other command as well. You can actually do that along with me in the playground. So now that I run it, I have the other record as well. Now when I run the resolve function, it's essentially going to return the winning bid to me, which will be the record that was owned by, the record whose bidder was B. So when I finish the auction, this is what my output is going to be. So I'm going to have the B record. But now how do I finish the auction? How do I declare? After I've resolved the auction, I know what is the winning record. So when I call my finish function, the input to the finish function is the winning bid. When I take that as input, I just get an updated record where I have given the ownership of the record back to the person who has won the auction. And when I run it, this is what I'll be getting. Let me run this for you in my local, where I have everything set up. So if we look at the step where I had actually run the resolve function, it actually returns this record to me, which is the record owned by B. So when I call the finish function, I need to pass the winning record. And when I run the finish function, all I'm doing is updating this field, declaring it as the winner. But now, when I look at a practical auction, I would also ideally want to have some functionality which gives me the reward, right? So what is the assignment or the takeaway for you from this would be to add a functionality to claim some sort of prize. I have listed down the steps of what you are supposed to do in a doc. Let me open that. So there is, you can add a new record within your program called price, where it has a field called owner and a field called amount. Whatever is your bid can be the amount, or you can choose a random amount as well. And the task is to write another transition function called claim, which takes in the input as the winning bid from the finish function. Finish function gives you a record, which is the winning bid, and you should be able to return a price record which declares who the owner of the prize is and what is the amount. Amount comes from the winning bid, and the owner is essentially the person who was passed in at the record. Now make sure that you check the prize only goes to the winning bid. So make sure that the right assert queries are inserted, and that's all you need to do. And you also need to deploy your program. So in order to look at the deployment, let me just switch the laptop and show you the deployment. Now for those of you, you can actually go to Leo Wallet's Discord, the link for which is there in the setup instructions, and get some testnet credits. And using that you can deploy. If you happen to not get enough credits to deploy, you can reach out to us on the Aleo Devs Telegram chat. I'll show you the link and we can send you the credits for it. But the process of deploying a program is pretty simple. All you need to do is go to your environment file, update your private key to the account in which you have received the testnet credits, and then you can simply say Leo deploy. It infers the balance from your account and gives you the estimate of the total fee, which is again in Aleo credits, and then you get a unique address at which it is deployed. And that's how simple it is to deploy. Now that was about the deployment part. Any questions so far? I know it's been a lot of dump of information for probably an hour.
So will it run from the playground itself, or you have to do a global?
Deployment cannot be done on Playground. Playground enables you to compile, experiment, execute any functions that you have. If you are looking to deploy on chain, for now you will have to install only Leo. If you look at the instructions, it also has the Snark OS guide. You don't need Snark OS installation for this workshop. Just Leo installation is fine. Yeah, please go ahead.
Yeah, the part I don't understand still is a little bit how that we work in practice, the different rules. So when we compile, we create what will be able to create the proof in the future. And then every time we call with a specific inputs, we are just creating the proof of this action. And all of this will be happening mostly on off-chain or through a prover.
Yeah, in this case, essentially, since there is not a lot of computation that you are doing, right? So you are not, I mean, it's essentially happening on the network for you, right? Your machine's not responsible for generating the proofs, it's the network. If you run a local node within your system, that is when you would be able to see how fast you are able to generate the proof. Because right now, you're not doing anything on chain. I mean, the function that you are running on the playground, there is no on-chain transaction. The one which I ran had 2 on-chain transactions. But to answer your question for proof generation, you do not necessarily need to run your own prover. If you look at the fee that gets deducted, that is based on both the computational activity as well as the on-chain state change that you are doing. Because in this case, I had an on-chain state change. Fee will be higher compared to a simple program where you're just trying to add 2 integers. Does that answer your question?
Yes, but I don't have. So, for instance, if I send to a prover all the inputs, like how is it?
You don't necessarily need to send it to the prover. The chain handles that part for you. It's not a manual process. When I mentioned that the transaction goes to a prover and then a prover sends the proof that goes to the validator, that is happening when you run your program. Like the node, like the Leo language handles that for you. You don't. If you want to do a custom prover, there are ways to achieve that. But for now, since we are not running our own node, we are not configuring any new provers. And it's, I mean, when you run a custom prover, the process of running will be slightly different. Because you will have to configure which network you are deploying on. If you see here, there is an endpoint. And you can also configure, when you are running your program, how and which node you want to run on. You can specify a local host where you can run your own node and your own VM.
But in practice, if I were to run an actual auction, I would need to run a prover, right? Because I could not send to someone else to generate the proof.
If you cannot run your prover, you actually pay the credits. So the network incentivizes the provers who are running the nodes for you.
But how you trust them to not leak the information? That's the part I don't get.
Yeah, so if you do not trust them, you run your own prover. But if you trust the network, you rely on their services. And if you look at it, this the total credits that you are spending has some share that will go to these provers who will generate the proof for you. And I mean, if in case your program or your application is specific, where trust is an important aspect, you can run your own prover. In this case, you are relying on the network. That means, let's say 10 people in this room are running a VM node, and then there are, say, 100 other validators. So you are trusting those 10 people. A validator can also be a prover. So you can be both a validator and a prover and can earn more credit. So it's more of a incentivization play. Whoever is getting, like essentially what happens internally is that these provers bid, who picks up and generates the proof, and then whoever's the lowest bid, the highest bid ends up winning it, and that's how the estimation for these credits come. But if you look at it, you are doing an operation, say on testnet or mainnet, you don't need to run a prover because the network is live and there are a bunch of provers already available. We're obviously looking for more provers, so if you're interested to run a prover node, there's an incentivization program as well. But the insight I gave you, or the life cycle I gave you, was to help you understand how transaction moves in the network. You don't need to run a prover node to do anything. It's handled by the network for you.
Just not clear to me which part of the code runs in which part. I understand all the utilization, but I don't understand how am I transaction is private, if I have to send it to the network, right?
So when you're sending your transaction to the prover, they also cannot see your inputs or whatever you have marked as private. Their job is to just generate a proof that is understandable by the network, because they will receive the Aleo instructions that there is some storage called register 0, register 1, where these variables are lying. Your job is to make sure that this is happening. They cannot, for example, when I was doing a plus b is equal to c, my c was private and so was the variable b. They can only see a, and there's no additional information that I'm supplying with it. So as a result, when it goes to the prover, it's still a private transaction. And they cannot decode it. The decoding happens when you're trying to verify that this works. And again, when I say there's a public-private key pair and there are private records, there's also a concept of view key here, which makes sure that if you want your records to be seen by specific people, you can tell them that this is the view key, this is how you can go and make sure that this application works for you. But it is private because the prover generates the proof on the logic and not on the actual values.
Yeah, I think that's the main point. Yeah, so it's only your private input is only used when you verify in the end. So then you can say, okay, my A was public, which was 5, my B, which was private. I say that it's 3, and then you know the result of it. That okay, 8 is the right answer.
But for the second side, there are two ways. Like you can either, if you are trying to go to private states, like records, you can either create the part of this, like dimension, and send it to the prover directly, and the prover verifies it. But like for mobile apps, it's not always possible to generate even the small proofs. So there is an option called third-party delegation. So you can delegate your proof generation to the servers, like the wallets, the Leo wallet, maybe you saw them. They are part of this project. And you can delegate your proof generation to them, but in this case, you need to trust them.
Yeah.
So you can either generate your own states when it comes to private states, or you can delegate your
Yeah, it's like if you have
generation.
a huge machine learning computation that you want to generate a proof of that I did everything correctly, you probably cannot do it on your laptop. Then you need a special hardware for that. That's where the delegation of the proof comes in. Then you can trust them in that process. But I wonder, like, even in that case, you just have to trust them that they generate the right proof. You don't have to give them all your public, all your private data, right?
But they need to create the private record for you. So
Yeah.
you need to give them your credentials, but even in the worst case, you're going to lose your private, not the private, because of you.
So
Yeah.
what he's saying is that if you're, so I mentioned there's a concept of view key. What that does is it gives you the option to decide who can see the record and who cannot. So essentially, if you have to delegate this job to someone else, you would have to supply that to make sure that they are able to do the function that they're supposed to do. Right now, you're relying on the computational capabilities of your machine when you are running this program. Since it's a very simple one, it ran pretty fast. But let's say if you try running a machine learning application and your machine's not capable, you might see that the program gets stuck because the proof generation's not happening. Or it can take longer. So maybe as an exercise, what you can do is like have probably maybe 1,000 bits and try to resolve that in a function and see the changes in the computation time. So more the logic, more the heavier, like the proof generation is heavier. But the thing is, since you're not doing all of this on chain, you can practically let it run for a longer time, depending upon the computational capabilities of your machine. And once the proof is generated is when the on-chain part would get triggered, which is where you would get an estimate of how much Aleo credits you need to pay, so that whatever proof generation happened in your machine can actually go on-chain. Someone can validate that and then have that as a transaction within the pool to be able to validate and send it to for further propagation. So that's how it is happening for this example, because you are relying on the network, whatever is the current network state. So essentially you are generating it.
Does that answer your question?
I feel like there are several paths. If I understood correctly, but maybe I understood it wrong, is when I create the code, then I compile it, I create this compiled version. When I give to a prover, I give him a record that I create plus the code that I compile, and it generates proof from it that it moves to a new state of the record, but the record doesn't contain in clear everything I don't want in clear, right?
Yes.
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 And so then that can go on chain, so that this record was probably moving from this position to this position,
Right.
without showing anything, and only using the view key or something, I could show what was in this record initially.
Yes, yes.
So-
So this is when, let's say you are doing a transaction and you want to make sure that, let's say you're working with a payroll management system where you would want to make sure that which employee is getting paid is visible, but how much they're getting paid is not visible. So that's something you can control with the records, where you keep the name of the employee or their ID public, but the amount that they're getting paid can be a private aspect of the record.
And that's what I send to the prover. I send
Yes.
the name and not
Yeah, no, you essentially send the whole record. So when you create the record by default, everything's private until you specify you want a specific attribute to be public. If you call it public, it will be public. So it's like an access modifier.
I see. What you say is the blockchain is mostly useful at the moment you will have to store already the information, because most of the transition will be just proof on top of each other.
Yes.
And then we just, from time to time, what you call finalize,
Yeah.
store some specific record.
Right.
for
So all the transitions that are happening are off chain, right? Until you want to finalize the async calls. Async calls, when they get finalized, is when you publish them on chain. So you use something called as an await call. So you await the future record that was created, consume it, and push it on chain. Until you want to push it, it's essentially, the state change is not happening on chain unless you are using the finalize keyword. And as long as you are doing transition, think of it as doing computation. When you are trying to finalize something, that's when you are, let's say, think of it as pushing that state change on chain. Because in real world applications, if you look at, say, DeFi application, right? I am a DEX and I've done a swap, say, through a particular route. I don't want to store all the state changes of my swaps on chain. But what I do want to maintain is the initial and the final state. So whatever transitions my record would have gone through, I would want to skip the intermediate ones and only finalize the last swap and have the final state available. So what that makes sure is that when you're working with private applications, the overhead of proof generation and the complexity of that is abstracted out of the chain. So you can still do all of your computational activity with either cloud resources or GPUs and save the cost of gas and the overhead of long running times on chain. So you get the best of both worlds.
Got it.
Yeah.
And can we see the code you've done on your most advanced version? I didn't
Yeah,
show you the links.
I'll have this presentation as well, but this is where this advanced code is. It's called tinyurl.com/auction on Aleo. And for those of you who are interested to participate in the Learn to Earn part of this workshop, I'll quickly walk you through how to submit your GitHub, as well as what's the process for submission. So you need to go to aleo.tools and do a very simple signing message so that we can make sure that you've actually deployed the contract and it's your account from which it came. So once you go there, put in the private key from which you've deployed your contract and then sign this message called successfully deployed, and you'll get a signature hash. So the Google form that will be given, you'll have to input this so that we can verify that you've actually done the work. That's just how simple it is. Now when it comes to getting the credits, let me show you how to get that as well. You can go to Leo's Discord. Leo Wallet has a Discord, the link for which is also there in the set of instructions. Go to this channel called Testnet Faucet, request for faucet, and enter your address, and you'll get 11 or 10 or 11 test credits. And you can request credits every 24 hours. So this was the process of getting the credits. Now when it comes to what wallet to use, you can actually use any wallet. I'm using Leo Wallet, which is the native wallet, but you also have the option of using another wallet called Puzzle Wallet, and then there's another one called Away. So you can use either of them. Each of them have their own faucet. So you can request testnet credits from anywhere. For Leo, we have a Discord service through which you request it. So coming back here, so Leo Wallet, you're already aware how to request it. Puzzle Wallet looks something like this, and Avail, I mean all of them are pretty straightforward UIs, so it's just your preference of what you want to go with. Now in order for you to submit your task to be able to qualify for a reward, you can submit it using this Google form. It's a simple Google form where you just have to submit the GitHub repo and the signed message for you to receive the reward. Let me quickly show that as well.
And the repo is the basic.
You can clone.
Augmented with the claim function, right?
Yes, and I'll have this task shared with you as well. This is the task. So Google form is pretty simple. You just need to submit the GitHub repo. Make sure that you have the deployment ID as well. Your email, make sure it's the same as with which you registered at Luma. Then your address, where you want to receive it. You also need to do some sort of KYC for it's the process. The GitHub repo, the signed message, which is nothing but a signed message from your private key, and your transaction ID. When you deploy your program, you get a transaction ID for that. And that's all you need to do. And if there are any questions that you have, you can reach out to me or on Telegram, or you can reach out to the Aleo Devs channel. I'll show you the links for that in case you run into issues and don't have enough credits. But if you are someone who's interested to build on Aleo and have any idea, we are here to support you. We have an open grants program, so you can submit your idea and then have a call with our team to understand how we can best support you in building what you intend to build. And obviously, we'd love to see you at more future hackathons and our online initiatives that run across the year. You can scan it for anyone who's interested. It's updated. I don't have the link. And these are some useful insights for someone who's looking to get a little deeper insight into how Aleo works. There's a repo that we've curated called Awesome Aleo, which has pretty much everything that happens in this ecosystem. And this is the Telegram group for Aleo devs. So you can join this, and we should be able to resolve your query if you reach out to us. Like, query can be anything. If you are running into errors, you're running into installation issues, or you don't have enough testnet credits, feel free to reach out. And that's all for today. Thank you so much. And if there are any questions, please feel free to ask them.